Hey guys, this is going to be a very short video on the idea of curve fitting when it comes to experimental physics. So if we start with some arbitrary data, call it x and y, and we have some points here, which we don't worry too much at the moment where the points came from. There's data of some kind. So you can see, just by eye, that there appears to be a straight line which would fit straight through the center of this data. So that line goes by many names, but it is usually called a line of best fit, and just like a regular straight line, it has an equation, something like this, y equals mx plus b, where m is the slope and b is the intercept. In this case, it looks like the intercept might be right about at the origin. And this line, you could probably eyeball it and say that, okay, well, it's about here. And then based on the parameters of this line, you could find out what m is and what b is, and then you would say this line fits the data. But in physics, we are usually concerned with things that, rather than just arbitrary parameters x and y, these are actual variables which come from some experiment, say t and x, where x here I mean position. So then instead of this equation, where this is y and x, we can now call them what they are, position and time, and then I've left these two parameters arbitrary. So if you look into your textbook, there is an equation in chapter 2 which looks like this: x final equals x initial plus v times t. This is in the textbook's notation. And if you look, this is the same thing as this, with the following identifications, and that is that the slope is identified with the velocity, and the intercept is identified with the initial x position. So in this manner, we can use the data, which we've taken in some way to get the x and t positions. We can take this data and figure out the parameters by using what's called curve fitting. And so there are ways of doing curve fitting by hand, but in this class, when I say curve fitting, I mean the following: using a computer to find the best values for parameters. In this case, the parameters will be different in each situation, but in this case, parameters are v naught and xi. In the next slide, I'll do another example. The phrase best fit, best values, in this case is a very technical mathematical term which we won't worry about too much, but in other words, it makes this line look like it fits the data the best. So that's what I mean by best values. So in the previous slide I discussed linear fitting, meaning straight line fitting, but in many cases in physics we were going to see things which are curves that are not straight lines, so we need to discuss nonlinear fitting. So for example, we might have an object and we want to measure its time and its position as a function of time, and maybe we'll get the following data. Now obviously this data does not specify a line. For instance, if I said here is a line that goes through this data, there'd be a bunch of points up here which don't lie on the line, and then a bunch down here. So this obviously can't be a linear fit. But maybe you can look and see that it's something like a parabola. So let me try to draw a parabola on this roughly. Yeah, so that looks like a parabola, and so you might be convinced that although some of the points are not exactly on the line, due to the fact that taking data doesn't give you exact numbers, there's always some imprecision when it comes to data, you might be convinced that this is a parabola. So if you want to do something similar like we did in the last slide, you need to start with some kind of equation. And so here's the general equation for a parabola. General in the sense that a, b, and c are the parameters. We don't know what they are. T is the value here, and then the position is the value here. So maybe you could use your computer program. So remember, the computer program is what is going to tell you the parameters a, b, and c. I'm not going to ask you to find these by hand. Sometimes they're impossible to find by hand. We are generally going to use a computer program to find them. These are often called fitting parameters. So that's fine. We could fit this line and we could find a, b, and c. But of course, this is a real object. So this A, B, and C has to correspond to some real values, just like in the previous case, we had the velocity and the initial position. So if you look in your textbook, there's an equation that looks very similar to this, and that is the position is 1/2 at squared, where a is the acceleration, plus v naught t, where v naught is the initial velocity, plus x naught, which this is the initial position. So this is basically the equation that we had before, and then an additional term due to the velocity. Due to the acceleration. So in the next class period, we are going to be using nonlinear and linear fitting, and doing some things like this to try to find the acceleration, the velocity, and the initial position of some objects. In this lab, we're going to do falling objects. In later classes, we're going to do some colliding objects or some thrown objects. Of various things. Doing the fitting is pretty simple. Just remember that you do that on a computer. You get these variables on a computer, but what you're going to have to do is figure out how to associate this equation with the physical model, which we say describes the motion of real objects that we've been studying. So essentially what we're able to do now is we have two different kinds of activities in this course. We have whiteboards, which are telling us about the theory of physics and how to describe motions via equations and physical laws, and we have experiments. So the experiments serve to verify that the physical models that we construct using theory actually describe the real world, because of course that's what physics is supposed to be able to do, is describe real objects in the real world.